Hello. So today I'll be talking about the ODEs, and I will discuss the integrating factor method to solve first order linear differential equations. So let's start. So first let's discuss the general classification. Well, in general, the first order ODE, linear ODE, can be written as the following. So we have dy dx plus some function px times y is equal to fx. It is important that p and f are just functions of x. So we assume p and f are continuous. So basically they are nicely behaved. You can think of like sine functions, polynomials, exponentials, but not necessarily piecewise continuous. They just say continuous, or at least they are continuous in the intervals that we are interested in. Okay, so the goal to find y as a function of x. Okay, so how are we going to do this? Well, we're going to do what is called integrating factor method. Meaning multiply equation on some unknown function mu x to get the following. So first we're going to write, if we multiply, we obviously get this. To write the following. So the left hand side will be equal to derivative of the product function of mu x and yx. And this should be equal to mu times f. Okay? Well, that's good. But the thing is, this has to satisfy some rules, right? The first is, if I take the derivative of this one by the chain rule, then I get that d mu dx times y plus mu times dy dx is equal to mu x times fx. Okay, so let's see which terms are present in this equation and in this equation. Well, this one is here and this one is here. Okay, so that's good. So this one is here and this one is here. So in order to be equivalent, we gotta have that this term should be equal to this term here. And for this, we have to have, in order for this equivalence to hold, we have to have that the coefficients of y, the mu x times px, is equal to d mu dx. Okay, but then this is easy to solve, and this allows us to get what possible mu's we can have. And we solve this simply by this, or let's just write like this, d mu over mu, and we can just integrate, and we get integral of p with respect to x plus some integration constant c, and we get ln mu x. Okay, and if we exponentiate, we get that mu x is equal to exponential integral of px dx plus c. C can be arbitrary. One can take it to be 0 as well. But I will leave it because sometimes you might want to have it to write integral of px dx in a nicer form. But usually it's set to 0. So this is mu x. So we already found what mu x is equal to. But then we had this equivalent equation, which was much simpler, which was this. So let's just copy it. So we had ddx mu x yx is equal to mu x fx. But this is very simple to integrate. We have mu x yx is equal to integral of mu x fx with respect to dx, and another integration constant c1, which depends on the initial conditions. And then basically we bring the mu x to the right hand side and we get our solution. Yx is equal to 1 over mu x integral of mu x fx dx plus c1 over mu x, where our mu x was, as before, the exponential of px dx plus c. So as I said, c is free to fix. The one can fix in arbitrary way and as you please. So I may set to 0 and it will work normally. But I have like family of available options for me. So I will just circle this and to have this as our solution. So this is basically all there is to integrating factor method. Let's just do one example and let's wrap it up. Okay, for example, let's do like simple example. So we have dy dx is equal to 2y is equal to exponential minus x. Okay, so our mu x, according to our procedure before, is exponential times px, right? So let's identify what is p. Well, this is my px, which is constant, and this is just my fx, right? Okay, so let's integrate. So I'm going to get 2 times dx plus c, which I'll fix. So I'm going to get exponential. So indefinite integral of 2 dx is just 2x plus c. And I'm going to fix c to 0, c to 0. Let's write fix as well. So I'm going to get exponential 2x. And that's it. So that's my mu x. So let's multiply our equation. I can plug it in right away into this, but let's make sure that like we get our method clearly. So I'm going to multiply on exponential 2x dy dx. Then I'm going to write 2 exponential 2x y, and I'm going to have exponential 2x times exponential minus x. So they will combine. So let's write here. So multiply on mu x is equal to exponential 2x. Okay, so this is clearly, the left hand side is clearly derivative. So the dx is equal to exponential of 2x y, derivative of this. And the right hand side is just exponential of x. Okay, and then I have exponential of 2x. I will write it differently because it's nicer. Times y is exponential of x dx integral plus c. So my yx is 1 over exponential of 2x times exponential of x dx plus c over exponential of 2x. So that's it. And let's wrap it up here.